if you believe by hiding things you're making them secure, you're deluding yourself and you're making a very dangerous product. The reality is you should always assume the attacker has all of the documentation. You should always assume they have all of your code base, so they've bought a device, they've flipped it, they've extracted all of the code base. And you should assume they have infinite time because there's a lot of them out there. If you can make it, somebody can break it, and that's the reality. So instead, what we have to do is develop architectures and implementation where the only thing that we have to keep hold of is the keys. So that if a device is broken, okay, they've got one set of keys, but that is unique for that device. If they want to break another device, they have to break it all the way down, they have to pivot again to get the keys out, and of course, that's financially not viable for the attacker, it's hard for the attacker, and hopefully they'll find another target. So, how do we do this? Well, we need to have a broad understanding of concepts and limitations of the technology, how we develop cryptography, understanding how ciphers and standard solutions like AES work is great, symmetric versus asymmetric, signatures and certificates, authentication, fingerprinting. If you can understand all of that, then you're in a great place. Alternatively, you can leverage the APIs that are available with Synergy, and it'll get you through the problem an awful lot faster. So if we look at enabling confidentiality, true confidentiality can only be mathematically provable. In that, we can use cryptography to mathematically prove that a system cannot be broken. Synergy is bringing this premier cryptography to the MCU domain. It accelerates performance, reduces our power, and it gives us a lot more simple API. What we've got up here is obviously all of the different engines inside the Synergy security engine. We've got our true random number generator, we'll talk about that in a second, AES, DES and symmetric, asymmetric, some other symmetric components here, SHA-1, SHA-256, MD5G hash, and RC4 string cipher. And then we have our secure key storage over here as well. Benefit of this gives you minimal attack surface. Because the CPU is not operating directly on the data, you can reduce the amount of information leakage in the system quite substantially. It's got some integrated alarms, so in effect it's got a state machine in there. If you try and attack it, force it to start leaking information, you'll actually trigger a bunch of alarms. And that can then be used to like brick the device or throw it into an exception handler and prepare a response to that, which as I say, may be to brick it, it may be to reset the device to thwart the attacker that way. And of course it's got this very simple API. First of these blocks at the next level of information. So entropy is very critical to secure systems. Cryptography relies very heavily on complex and variable keys. In the secure boot process, which we have developed in concert with Renesas, we develop a very highly random 512-bit seed. And that 512-bit seed then goes through a set of key derivation functions to produce the key. If your true random number generator is not high entropy, those keys themselves will start to leak information very, very quickly. In terms of this block, it's NIST SP 890 compliant. This is the latest specification for entropy. It really is the best in class. And again, it's worthwhile really focusing on because this is a true differentiator for Synergy and it's a true differentiator for platforms leveraging Synergy. If you're not using a true random number generator, you're using a pseudo-random number generator, the likelihood is somebody will break you relatively quickly and relatively easily. So, I can't stress enough how important this block being right is. It's managed within the Synergy security engine. Software attacker can't easily force it or manipulate it. This is a standard attack on devices. If you can get in and you can force the random number generator, either through heating the device, cooling the device, changing voltages, then you can start to break down the devices. You reduce the entropy and you reduce the amount of attacks that you need to figure out to make it work. So the fact that we guard against all of those makes it a true random number generator a really key part of this. And it's very, very easy to use. So the nice thing as a Synergy user is, it's there, you know it's there, but you don't have to really understand the technology which is making it work. You can if you want to, but all we have to do to read it is a very simple function call. So, as I say, we support in Synergy all of the major symmetric crypto blocks. From a IoT perspective, again, really AES 128 should be your absolute baseline. While it's great to have things like triple DES included in Synergy from a legacy perspective, it's not where you should start any system design today. Of course, symmetric cryptography uses identical keys for encryption and decryption, so the stakeholders must implicitly trust each other, and keys have to be shared in advance to avoid attacker access. So we have some powerful cipher support here. AES should be good for industrial applications for 20 years. Low power, simple application. In terms of AES, again, some really nice, simple function calls here. So in terms of setting the key, We just, literally need to bring it in. We've got the key itself, key length, key schedule, and that allows us to define which of the key lengths we're going to use here. And then in terms of the actual encryption, again, very simple function call: what's its length, what's the plain text in, and what's the cipher text out. So we don't need to know a lot about what's going on inside there to actually start using cryptography. This table is incredibly important. Cipher agility is going to be one of the big challenges of the next 20 years. The nature of ciphers is they run out of time. We have people attacking them, whether it's quantum attacks or whether it's just brute force attacks. Eventually, AES-128 will not be sufficient. So what do you do? Well, you can either go and buy a new chip. That's okay, I guess, and it's a good business model to sell new stuff. But if something is deeply embedded, then we need to be able to move it forward. And in this case, with the Synergy devices on the 7 and 5, we support 192-bit, which you may want to go to because it's obviously a slightly lower performance hit, or alternatively the 256-bit. So we have crypto agility there. We also have a bunch of chaining modes. These are really, really important. The basic ones are CBC and EBC, electronic code book and cipher block chaining, which allow us to add lots of different encryption packages together. We also have the CCR and the other ones. And again, all of these main chaining modes are included. If you look at competitive solutions, they will normally have one of these. We won't have enough capability in there to deter attackers over the long term. You may also, if you think that you're being attacked, you may want to change the chaining mode at some point as well. So these are additional protections in the framework of how we think about security. In terms of the asymmetric ones, of course, the whole nature of asymmetric is that the public and private key are different. They're generated through a trapdoor equation, which is very easy to do in one direction, but very difficult to do in the other direction. So in the case of RSA, you can generate two primes, you can multiply those together in a modulus way, and you can come up with an answer. But taking that answer and trying to regenerate the primes is incredibly difficult. Now, you then generate, obviously, the public key and the private key. Doing this doesn't necessarily mean that the message came from a trusted source. It just means that somebody's got your public key. So you do have to be careful, of course, that just having the cryptography on its own doesn't prove that the message is correct or it came from the right place. It just means that somebody has the key. Again, lots of advantages of having it in the secure engine. But fundamentally, again, as probably many of you know, it's an and between asymmetric and symmetric encryption. Asymmetric is very challenging, it's very computationally expensive, even with an engine. So this has to be focused on authentication of devices, onboarding, creating secure channels, whereas symmetric encryption is ideal for very fast, low-power encryption. But once you've got the key, you've got access to everything. So really, from a security perspective, it's an and. Again, I'll refer back to hopefully what some of you saw on the show floor yesterday, where we had the secure boot mechanism for uploading new firmware into a device. The way in which we did that is that we took the binary for our code and we encrypted it with a 128-bit key, which is really, in effect, just a high-entropy random number. It's just been generated on a PC. That key in and of itself, is temporary. It doesn't exist for long. What we have to do, though, is we can take the encrypted blob, we can fire that across the internet, it's encrypted, so it's fine. But then what we have to do is we have to take that symmetric key, and somehow we have to get it to our manufacturing line and onto the device. And we use the asymmetric component to create a very strong tunnel between the device which is delivering the keys and the inside of the chip to create that secure, robust tunnel which we can then inject the symmetric key through. So on there we also have the hash block. We use hashes for creating unique fingerprints, and really it helps us prevent modification of data. So this would be things like a man-in-the-middle attack or a replay attack, where there's timing modification. So a very simple example of this, again, if you guys know all about hashing, I apologize, but for the people who don't, here we can see two sentences which are the same apart from one letter has been slightly changed. The nature of a hash means that the output when we do the hash is radically different. And in most cases, there is sufficient differentiator there. If we use SHA-1, it is theoretically possible today to create identical hashes. If we use SHA-256, which again is part of the NSA Suite B capability, then these hashes are sufficiently different and sufficiently robust that we should be able to protect against man-in-the-middle attacks, injection attacks, and others for the next 20 years or so. So there's a very good block there in terms of the SHA, the G-hash, and others, again, which allow fast operation and relatively low power operation. So let's look at how we're starting to set up a system. And confidentiality is critical here. So we may have a gym, we may have a running machine, we've got various different stakeholders in here, the actual athlete himself, people who have some responsibility for the machine, predictive maintenance, equipment leasing, gym ownership. Because of asymmetric encryption, we can share data with each of these independently without giving away the private information of the runner here. At the same time, we could use an envoying technique, perhaps with some personal keys inside the next generation smartphone here, to deliver those keys onto the running machine and tunneling through the cloud. That means that we could take this person's information and send it to his physician or his surgeon or others. And from my personal perspective, this is important. My father-in-law had a heart valve replaced, and he then had to go to some specialist gym sessions where there was a nurse in case he collapsed. Whereas if you could apply your personality to the machine in a secure way, you can share information a lot more broadly without surrendering any privacy. It's all about keys. It's all about key exchange and key management. So here's this example, and here's how we'd use Synergy for this. So we may need to do some pre-provisioning. So we perhaps have our watch here. So we're passing over a public key to our watch into our user cloud. We are taking